Great. Thank you very much, Zach, for the introduction. In this session, we will present a work related to the application of graph-based entity resolution techniques for intelligence analysis. Here you see the speakers of this session, Federica, Pantellis, and me, Giuseppe. We all work for GraphAware, which is a graph company that leverage globally recognized graph software development company that offers powerful analytics and data science expertise in the fields of graphs. During this session, we will provide you details about entity resolution and its role in the intelligence domain. Then we will show you two main demos. The first one is related to the usage of entity resolution for bank account analysis, while the second one is related to the lesson that we have learned in applying some specific strategies for entity resolution in a real scenario. Among these strategies, we can include, for instance, the change data capture. So basically the capacity of detecting incremental updates in the database and then perform some specific actions on a specific part of the graph which is actually affected by these incremental updates. And we will finalize this session by providing you some takeaways that directly come from our experience with ER. Entity resolution is particularly useful in the domain of the intelligence analysis, because in this specific context, we have to, there are some goals, including the validation of identities to clearly identify unique entities. For some specific scenarios, we want to mitigate the signal to noise challenges, specifically for the analysts. In many situations, we want to map the connections between the individuals and other legal entities, like, for instance, higher risk organizations. And if we consider the activity of police offices and agencies, one of the key goals is to build a 360-degree view of suspected cases by combining data from siloed sources. Reaching this goal, it's not an easy task because we have to address some issues that are related to the quality of information. As we already mentioned, we have to manage data coming from heterogeneous sources. Sometimes we have to consider cases where no rigorous standards and manual forms are adopted for collecting information. If we consider large institutions, we have to face inconsistent data entry processes between, for instance, different branches, divisions, or different offices. And we have also to take in consideration diverse identification systems and practices that can be adopted, for instance, in the same office. This is a typical situation in which the entity resolution comes to play, because the goal of the entity resolution is to draw connection between these scattered, incomplete, and potentially inconsistent records with the goal of resolving entity profiles. And if we successfully apply entity resolution, then we can create unified and complete view of different objects, such as accounts, organizations, and so on. We can reduce the complexity because we are able to manage with normalized data on the one hand, and on the other hand, we are able to reduce or remove duplicated information coming from multiple records. If we are able to achieve a high quality source of data, then we can perform more accurate analysis and prediction, and at the end of the day, perform better decisions. This is a simple flow for the entity resolution process. The first step of this flow is connected to the data ingestion phase. So basically, we have to load information from multiple sources. In the second step, we have to compute similarities between the objects, so potentially the nodes that we have ingested in the previous step. And for computing this similarity, we can apply rules that can include and combine exact and fuzzy matching techniques. In the last step, we want to group these similar objects by leveraging, for instance, community detection algorithms. And in the further step, generate what we call the resolved entities, right? So basically the nodes in the graph they represent entities in the real world, whose information can be distributed, for instance, among multiple records that can belong to multiple and different databases. So I want to leave the floor to Pantelis for our first demo. In this demo, Pantelis will show entity resolution for bank account analysis. So Pantelis, the stage is yours.
Thank you, Giuseppe. So I will present you our work through Hume, GraphShower's graph-based intelligence analysis tool. And first, I will begin from the schema that we'll have and the use case that I will present to you. So in this demo, we are interested in resolving people connected to different bank accounts coming from different siloed data sources. And each of these person is connected to some addresses, emails, phone numbers, and social security numbers, which are their unique identifiers. And as Giuseppe said, we will perform some, we'll apply some rules on these persons to create similarity relationships between them. And then from these similarity relationships, we'll create person-resolved nodes through clustering by applying WCC, weakly connected components. So we'll do all of this using Orchestra. I will just show you an example of how our workflow looks. In this case, first we have a cleanup step to clean previously created resolved persons. And all of this happens using a Cypher query on top of Neo4j. So if I open any one of these components, you can see that it's Cypher connecting to the underlying Neo4j database. So first we delete the previously created nodes, then we get the clusters IDs of all the person nodes that we have, and batch them for efficiency, and then create the new person resolved nodes. So let me go to our visualization and walk you through the demo. So here we can see in blue in the middle the resolved node, Megan Allen, and in purple the other person nodes that have come from different data sources. So if you can see on the top left, we have a badge that indicates the different data source that each of these nodes come from. So in this case, if we look at the properties tab, we can see that this comes from a medical registry, while this person comes from a national registry. And we can see that they have a lot of information in regards to them, and also they are connected to bank accounts and social security numbers, etc. If we take a look at the relationship connecting these two nodes, we can see the similarity has a score of 1, so 100, and the reason why these are connected is because they have the same SSN. Let's take a more complex example, and in this case, we see that the score is lower, in this case, 76% approximately, and these are connected by same phone, by email, and have a similar name. The great advantage of graphs is that we can visually explain this relationship. So with a simple click through Hume actions, we can instantly see how this translates in the graph. So we can see that the email of one person is connected to the cell phone of another, and we can highlight it on our visualization as well to see how and why these two are connected. Of course, similar, we can get the similarity path for any two nodes on the canvas. This works similarly to like a shortest path. So in this case, let's reveal the similarity for these two people. And again, we can see the full similarity. Again, as you saw, this is returned instantly, while in relational databases, this would take a long time to return a result. Next, let's focus on the bank accounts. And for each of these persons, we can, again, through actions, get the returned bank accounts, the connected bank accounts, with a score based on the similarity of the person that they are connected to. So the first two are from the left cluster, basically, that have a score similarity of 1. And further down we go, the score and probability of one of these bank accounts being connected to that person decreases and decreases further. We can also again see it on the map. So let's, sorry, not on the map, on the canvas. So let's see how it looks. And we can see that highlighted, we have these three bank accounts. And from the other side, of the canvas, do the same thing. Do the same thing from the bank account and return all of them. And again, we can see all of the related bank accounts. As we see, there is a curious person in the middle with a different styling. This person, which is marked as ambiguous, and performs as the cutoff for these two separate subclusters of people. The one that is around Megan Elizabeth Allen, and the other one is Megan Taylor Allen. So, as you may know, a lot of these algorithms don't perform 100% correctly, so you might need to further verify and resolve situations manually. And in this case, we can manually delete the connection to this person, resolve and create a new one. In this case, it will be Megan Elizabeth Allen, and then create a connection between these two nodes to this resolved new node. So, of course, ideally, we want to minimize the manual effort as much as possible. And also, we can have more advanced ways to help us clarify this ambiguity that we have in the middle. So I will stop sharing and return the floor back to Giuseppe and Federica to show you how we can handle this. Thank you.
Thank you very much, Pantelis, for this demo. As you have seen, in this case, the impact of a graph algorithm is extremely useful in terms of results for entity resolution, but also in terms of explainability, right? As you have seen, thanks to the highlighted path in the visualization. However, in order to apply entity resolution in real scenarios, we have to consider some critical aspects that actually are related to each of these specific steps. For instance, in the case of the data ingestion, we have to consider the case in which we have to process our data set from scratch, so basically a full processing. But probably in many situations, you have just to manage and consider a small incremental step or process in your data, right? So you have just to manage a small updates in your database. Regarding the similarity computation, we need procedures that avoid and that allows us to overcome the issues related to a brute force approach and a brute force method. Because, for instance, when you have millions of nodes in your database, you cannot compare all these millions of nodes to each other. And regarding the final step, it's useful to be flexible in the usage of the weighted edges. So basically, the weights have been computed in the similarity step, but we can use these edges, for instance, just as a threshold for our connected component computation, like we do in WCC, or we can use these weights directly in the computation of the communities, like we do for Louvain. So let's see how we can extend this simple schema. As Pantelis already discussed, in order to process the full dataset from scratch, we have to apply some cleaning and initialization. But now I would like to focus in particular on the problem of scalability in computing the similarities, because instead of comparing, for instance, each person name to all the other person names using a similarity method, we can add, for instance, an intermediate operation, such as the full text search on News4j, in order to retrieve a set of candidates and then apply the similarity only on these retrieved candidates using the Neo4j index. And we will show you in a while some initial results that are promising, that show how this approach performs better than a brute force operation. The goal of this slide is just to provide an overview on the CDC or incremental processing. I don't want to spend too much word because Federica, we will show you in a while a concrete example of applying this specific process. I want just to clarify that the purple blocks are triggered in our case just on the situation of updated nodes, because allow you to apply some changes and deletions only in the subgraph that is affected by this update operation. For instance, we can remove the similarities because they may no longer valid after this updating step. While the blue blocks are triggered for both new and updated nodes, with the goal of marking the subset of nodes that must be processed using WCC and Louvain. So basically, only the affected subgraph will be reprocessed using these specific algorithms. So I will leave the stage to Federica. Let me unshare the screen. And Federica, the stage is yours.
Thank you, Giuseppe. In this demo, we will see how we can use Louvain for verifying the quality of the clusters, because so far we have applied a weakly connected component, and we will apply a change data capture approach in order to perform only few changes on the entity resolution process and perform again the entity resolution only on the affected nodes. So in this case, we have computed the similarity relations, and we can see them here. And we have also applied a weakly connected component in order to solve a group of connected person by using a person resolved. In this case, this group of purple nodes that are similar among them is connected to a single person resolved because it is a connected component. Then we have also applied Louvain, and we can see the results of Louvain algorithm by enabling the grouping strategy that we have in Hume, and we can observe that in this case, Louvain returns two different communities as belonging to the same connected component. This is a situation in which we can notice something strange, because Louvain returns multiple communities, because there are, in this case, two group of nodes that are densely connected. So indeed, we notice that on one side, we have 4 people with the same name, Doris Garcia, while on the other side, we have people that have a name similar to Jennifer Warren. So let's start the investigation, and we can check the reason why we have these links that start from the Doris Garcia community to the other one. We can notice that the method of these associated to these similarity relations is the same social security number, because indeed Doris Garcia has the same social security number as Jennifer Warren. And this is the same for all the relations that start from Doris Garcia going to Jennifer Warren. The social security number is the same. So we can check the situation, and by checking our registry, we notice that the social security number of Doris Garcia is wrong. So let's suppose that we want to update this attribute of this node. We can do it by using the graph editing, and let's say that we just forgot to add last numbers. So we can save the changes and submit. Now we have the new social security number, and what we want to do is to simulate the change data capture approach. In order to do this, we can use a Hume action that is a predefined cipher query that in this case is a local action, meaning that it works on the selected node, and it simply simulates the CDC by marking the node as to be processed again. Here we are adding a label. So let's run this action on the selected node, Doris Garcia, and now we can run the entity resolution, the incremental entity resolution, in the sense that we consider only the portion of the graph that is affected by the change of Doris Garcia, and we resolve the entities. We have implemented entity resolution by using Orchestra workflows. Orchestra is our orchestrator, and we have 2 different workflows. The first one deals with the old similarity relations, because in some cases these are not valid anymore and we need to delete them, and recalculate again this similarity. So let me run it in the meantime. But we can notice that this is composed by 2 branches, and once the first one finished, the second can start. And let's investigate these components. So the first component is a reader. So we are reading all the nodes that are marked as to be processed. And then after this step, the incoming message go over on the Neo4j writer component. This component essentially works by adding a label for the weakly connected component, because we need to mark the nodes on which we have to run again entity resolution. And we use disaffected label. Indeed, for each incoming message that is the node to be processed, we are adding the label as affected, and then the entire cluster connected to this person has to be marked again as affected, because since we can drop some relationship, a connected component cannot be connected anymore. And also the person resolved that is connected to this node has to be removed, because we want to calculate again, to create again this person. Then we remove the similarity relations, and then by reading again the nodes that have to be processed, we apply the rules for the calculation of the similarity. So in this case, we have two different rules. The first one is based on the social security number, while the other one on the date of birth. So starting from the first one, we can notice that here for each incoming message that is a node to be processed, we are just checking the condition for the creation of a similarity relation. And we are finding all the nodes that share the same social security number. Then we create the similarity relations, and for all the nodes that are affected by this new link, we are marking them as affected. And the entire cluster that is connected to this node is affected, because this node can now are now connected to the incoming to the our starting node, the node that we modified. And again, the person resolved connected has to be removed. Okay, now we can move on to the other workflow that works by it runs a weakly connected component and then Louvain. So let's start it. And it starts by removing the person resolved that are marked as to be removed. So essentially here we are reading, and then we can delete them. And then we project the graph by using the projection that we have in GDS. And we are using the label affected for projecting the graph on which we need to run the new algorithms. Also, we are considering, we are aggregating the score of the similarity relations, because we need them for Louvain. And the first algorithm that we run is WCC without considering threshold, without anything. So we just run the algorithm in streaming mode, and then we create the new clusters. We set, the property related to the community identifier. And then on the same projection, we run a Louvain that this time is a weighted run on a weighted mode. And the last step would be the creation of person resolved that are connected to these nodes. Now, if we come back to the visualization and I reload the data that are on the canvas, okay, let me disable the Louvain strategy. We can observe that each group of people that have similar names is connected to a different person resolved. And this concludes our demo related to the change data capture approach. And we have also seen how we can use Louvain for verifying the quality of the clusters obtained by using a weakly connected component. And back to Giuseppe for the scalability. Thank you.
Thank you, Federica. Let me share my screen again. So as you have seen from these specific examples, in the case of Pantelli's demo, the analyst was able to recognize ambiguous situations directly on the visualization, while in the case of the Federica demo, she applied Louvain in order to automatically detect these multiple communities inside a unique connected component. So we are going to conclude this presentation just by showing some initial interesting results, because as you can see in this slide, we apply a similarity computation by consider a fuzzy matching on the person names and an exact matching on the date of birth. So in our experiments, we noticed that a brute force approach required for 1,000 nodes, processed against the entire database, which include almost 3 million of person nodes. A brute force operation requires around 900 seconds, while a scalable approach that includes, for instance, and leverages actually a full text index. The timing was just 7 seconds for 1,000 nodes. Within a database of almost 3 million of person nodes. In the code here, you can see the differences. So how the match is replaced using calling a specific procedure for the full text search. And so we believe that these results are really interesting and promising. So to conclude our session, we can say that the entity resolution is an hard task. However, we can take advantages of graph-based analysis because we can apply multiple algorithms like community detection algorithms. But the graph is also useful, and it's also really useful for the explainability, right, of the results. And we notice in our direct experience that Neo4j provides all the necessary features for managing the entity resolution in real scenarios, because we were able to manage a huge amount of data on the one side, and on the other, we were able to apply some specific strategies for managing incremental updates. So I would like to thank you for your attention. And if you have any question, comments, or suggestion, we are here to answer for some minutes, and then we can answer directly in the chat. Thank you very much.